Forces on an incline. If a physics student uses a large ramp to lift a box onto the roof of a school, the box has a mass of 150 kilograms. The ramp is positioned at a 25-degree angle from the horizontal. The student pushes the box with a force of 1,000 newtons, accelerating up a ramp with an acceleration of 1.6 meters per second squared. Let's start with a force diagram. It looks like we'll have a force of gravity down, an applied force up the ramp in the direction he's pushing, a normal force perpendicular to the ramp, and a force of friction resisting its slide upwards. We can now draw these in more detail on our packet. We already know how to solve a problem like this by breaking forces into components. So we break the applied force, we can calculate the force of gravity. We don't know what the force of friction is, but we know that they're all at 25-degree angles. So now we can draw our force table. We can list the forces that we have available to us. We can figure out the components of the applied force, the vertical and the horizontal components, but the acceleration is up the ramp, so it's in two directions, which means that we have to find the acceleration vector and the acceleration components. So we'll go at an angle, we find the horizontal and vertical components of the acceleration, which means we can find the horizontal and vertical components of the net force. We use our net force equations, we find the net force in each direction. But then we do use our net force as the sum of all forces to have all of the individual forces in each direction, not each force in each components. So we have the net force in each direction, don't use some math to figure out this, but we have to find the component parts. We have two variables, two unknown variables, four variables, we go and all this in. It looks like this is just going to be really difficult. But this would be easy if there were fewer components. So let's imagine we look at our force diagram as it exists right now on the Earth. The force of gravity points down towards the center of the Earth, and everything else is adjusted accordingly. If we were to rotate the entire system and look at our force diagram afterwards, it looks like we would have three forces in the direction of our axes and only one force that's at an angle, and that angled force would be the force of gravity. So let's rotate everything 25 degrees clockwise, and we'll show this with a rotating arrow. This means we take all of our forces and rotate each of them 25 degrees. So our new rotated force diagram will look something like this. With our rotated force diagram, we can solve this problem like any force at an angle problem. Although the force of gravity will be at an angle, which is weird. Originally our acceleration vector was at a 25-degree angle. But when we rotated everything 25 degrees, our acceleration would be rotated as well. So our acceleration is to the right, 1.6 meters per second squared. Using our net force equation and Newton's second law, we can find the net force will be 240 newtons to the right. And to the right is actually up the ramp, because we've rotated our axes. Now we can start to fill in our force table. The net force in the x direction will be 240 newtons, but the net force in the y direction will be 0, because it's not moving perpendicular to the ramp, just parallel to the ramp. We have a force of gravity, a force of friction, an applied force, and a normal force. We can fill in the parts that we know will be 0. We can fill in our applied force, which we know is 1,000 newtons to the right. We can calculate our force of gravity, but our force of gravity is at an angle. It'll be at a 25-degree angle down and to the left. Calculate the components of the force of gravity now. If you need help with this, see one of the previous videos on breaking vectors into components. So as we find the components to our vector, we know that the horizontal component is leftward, so it'll be negative 634 newtons. And the y component is down, so it will also be a negative 1,359 newtons. When we rotated our axis, the x directions are the ones that are running side to side, so right will still be positive and left will still be negative. Although rightwards will actually be up the ramp, leftwards will be down the ramp, and y components will be into or out of the ramp, so perpendicular to the ramp. The net force is the sum of all the forces, so the net force in the y direction is the force of gravity plus the normal force. If we plug in the values we know, we can find that the normal force is equal to 1,359 newtons, and that would be upwards because it's positive, and upwards here means perpendicular to the ramp. We can do the same thing in our x direction, summing all the forces in the x direction and all the components. Plugging in the values that we know, we find that the force of friction is equal to negative 126 newtons, and the negative tells us to the left, or down the incline.